Thank you for watching this video. Today, I'm going to introduce a fast algorithm for one-bit compressed sensing and show that it has near optimal statistical guarantee. So we can think of this process as having two phases. So in the first phase, there is an underlying signal x that we want to take some fast measurements, and we can try to write x as a d-dimensional vector. Okay. Then a natural choice of measurements is linear measurements. So here we multiply x by a matrix A, and the size of A is n by d. So which means we have n number of measurements. Okay, and we note that in order to make the sampling efficient, we must have n much smaller than d. Otherwise, you just record all the pixels of x and you are done. So in the second phase, we try to recover x from the knowledge of a and y. And from equation 1, we know that this is an underdetermined linear system. So usually there are infinite solutions that are consistent with our observation. So that we have to impose some sort of constraint on x. And that is why sparsity comes in. Okay, so basically, phase 2 is tied to the first phase, and for different sensing matrix A, there are different recovery algorithms. For instance, if the matrix A is Gaussian, then you can apply lasso, orthogonometric pursuit, iterative hard thresholding, and other methods to recover X. And if A is a sparse matrix, let's say a sparse Fourier matrix, then you can go with count min or count sketch. Okay, so this is the standard pipeline for compressed sensing, but in this paper, we studied the one-bit compressed sensing model. So instead of recording the product A times X, we just record the sign of it. Okay, so here, the measurement Y is sign of A times X. And again, we have to assume that the number of non-zero elements of X is less than some parameter K. Okay, so we will consider the most natural estimator to recover the signal. So the objective function is basically the correlation between the input and the output of the mapping function. So here the mapping function is the sign. And we try to maximize the correlation. So the sparsity constraint comes from our prior knowledge that the true signal is sparse. And also we have a two-norm constraint because A, without the control of the two-norm, the objective function can go to infinity. That means this program is not well defined. And B, the sign function absorbs the magnitude of the signal, so basically we can specify the two-norm to be a constant. So here for convenience, we just say the two-norm is equals 1. You can also say, I hope the two-norm equals 10 equals 100. Okay. So this is basically a non-convex program. We know because the sparsity constraint is non-convex and the two-norm constraint is also non-convex. But surprisingly, there is a global optimum that is very easy to obtain. So the solution is very simple. So first we calculate a vector V, which is given by A transpose Y. Then we perform hard thresholding on V. So hard thresholding means we keep the k largest absolute elements of V and set the remaining to 0. And then we just normalize the hard thresholded vector to unit norm. Okay, so such solution was discovered before, but there is no statistical analysis. Okay, so this is our main result. So we assume some standard conditions. These conditions are a little bit technical, so you can find it in the paper. And we show that with a high probability. The distance between the global optimum and the ground truth signal is upbounded by root of k log d over n. So that implies that the sample size is proportional to k log d, which is near optimal. And it's also worth mentioning that we can make the success probability as large as 1 minus d to the power of negative c for any constant c. Say you can let c be 100. Okay, so I want to sketch the proof because it's very simple and the proof illustrates how can we extend the results to handle different types of signals beyond sparsity or different sensing matrix A. Okay, so first of all, we know that the ground truth signal X is a feasible solution to the non-convex program. And we also know that X hat is the global optimum. So that means the objective value evaluated at X hat must be greater than that of X. Okay, so that gives equation 4. And then we consider a positive value lambda. So later on, I will show you how to pick this value, but for now, our proof goes through for any positive lambda. Okay, and we do a little bit of arrangement, so equation 4 becomes equation 5. This is sort of fundamental calculation. And we look at the left-hand side. So we know that the 2 norm of x equals 1. So the left-hand side is given by lambda minus lambda times x hat. And furthermore, the 2 norm of x hat equals 1 as well. So we just multiply the sum of their 2 norm and then divide it by 2. Okay, so this guy essentially equals a scared value of the distance between x hat and x. Okay, and for the right-hand side, it's very simple. So we just apply Hodl's inequality. So it's less than a infinite norm of this guy times the 1 norm of the difference between x hat and the x. Okay, so then we can combine these two results and show that the quantity of interest, which is the difference between our global optimum and the ground truth, is bounded by 3 quantities, basically. The first quantity is gamma, the second quantity is rho, and the last quantity is lambda. Okay, so it's bounded by gamma times rho divided by lambda. Okay, so for gamma, it's not really hard to bound this value because we can think of gamma as sort of infinite norm of a some average minus lambda x. And if we can take a lambda such that this average centers around lambda x, then this is sort of concentration. And we can apply, let's say, Hofstad's inequality to bound it. So in fact, if the matrix sensing matrix A is Gaussian, then we can show that gamma is bounded by root of log d over n. And if you go with different sensing metrics, say if you go with sparse Fourier or you go with heavy-tailed distribution, then you just need to recalculate the gamma for these metrics. Okay, and for the quantity rho, we know that there is a very general upper bound for it. Rho is upper bounded by root of the sparsity of x hat minus x. And this one does not depend on the sensing schema, it just depends on the structure of the signal. And in our case, both signals are k-sparse. So rho is bounded by root of 2 times k. Okay, but of course, if you have more information on your signals or you are considering different structure of the signal, then you may have better bound than this one. Let's say if you know that the signal is alpha strongly decaying for sufficient large alpha, then rho is like a constant. So that means the sample complexity to recover the ground truth signal is like order of log d. Okay, thank you so much. And you can find more details in my paper.